Hello everyone, and welcome to the second lecture of the Reliable and Interpretable Artificial Intelligence graduate course taught at ETH Zurich. My name is Martin Vecev and I'm professor at ETH. And in this lecture, we're going to be focusing on adversarial attacks, so generating adversarial examples. So before we get into the whys and hows of generating adversarial examples, I wanted to mention this article that appeared a couple of years ago in the communications of the ACM, which is called Human Level Intelligence or Animal-like Abilities by Adnan Darwish. And one of the interesting quotes in the articles is the following. It says, we need a new generation of AI researchers who are well-versed in and appreciate classical AI, machine learning, and computer science more broadly, while also being informed about AI history. So essentially what he's mentioning and referring to are, kind of the topics that, this course covers, which is combination of data-driven learning-based optimization and symbolic methods. So just another data point that supports what we're trying to do here. So the plan for today for adversarial examples is the following. First, we're going to show a few more examples in various domains, various application domains beyond those which we showed in the first introductory lecture. We're going to discuss why adversarial examples exist, and then we're going to focus on techniques for generating adversarial examples, both targeted attacks and untargeted attacks. Okay. One thing to mention here is that the techniques that we're going to be looking at are going to be useful not only for generating adversarial examples, but also later when we're doing adversarial training, incorporating background priors, provable training, and so on and so forth. Okay, so just keep that in mind. Another thing to mention is that from now on, the course tends to get more and more technical. So, after the examples, we're going to start looking at more technical things, and then gradually it will just stay like this. Okay. So let's look at adversarial examples. So here's one definition by Young Goodfellow, one of the co-authors of the well-known deep learning book. What he says is, adversarial examples are inputs to machine learning models that an attacker has intentionally designed to cause the model to make a mistake. Right? Now, whether you have an attacker or you don't have an attacker, you just want to check how good your model is. This adversarial examples would still be relevant. That's a fairly high-level informal definition. And from last lecture, we already saw these examples here, adding imperceptible noise and getting the model to misclassify the panda to a gibbon, putting stickers on stop signs and getting the deep learning model to predict that it's a 45-mile-per-hour sign, a speed sign, and on the bottom right, having these three different neural networks, each misbehaving in a different way in the different pictures. Basically, one of them always tells to go to the right and the other to say to go to the left. Okay. While in each of these cases, most humans would, even children, would be able to tell what the right classification, what the right decision should be. Let's look at a few more examples. Settings where adversarial examples are relevant. So just so you don't get the idea that there is only noise-based perturbations to the pixels of an image. For instance, geometric transformations, geometric perturbations. You could also talk about adversarial geometric perturbations by, for instance, taking an image like 7 here, labeled I0 on the left, top left, and rotating that image by some degrees, in this case, negative 35 degrees. So in the first case, the network correctly classifies the image as 7, while once we rotate it and obtain this adversarial image, right, that looks like a 7, or somebody can even say it's a 3, but it's kind of more like a 7, right? So the network classifies it as a 3. Now in practice, this, when you do rotations, the images, the adversarial images that you obtain, which lead to a misclassification, actually can be achieved with much smaller values for the rotation angle, just few degrees to the left or to the right. So they really look like what you look like a 7, but it gets misclassified to some other digit. And one point to mention here, which I already mentioned in the first lecture, is that when you're generating adversarial examples, you may be generating them right at the input of the deep model, or you may be generating them at the start of some pre-processing. And once the pre-processing is done, the output of that pre-processing would go into the deep model, but you'd be changing the input of the pre-processing or the transformation before going into the deep model. And this is an example of this setting here, where you are trying to figure out angles by which to rotate the image, so that once the rotation transformation has taken place, and that's an example of some form of pre-processing, then the resulting image gets misclassified by the network. So this type of pre-processing happens in various settings. Maybe there is a computation of the embeddings in NLP. Maybe there is audio processing, as we'll look. Maybe there's geometric transformations and many others. Right. So that's one point. Here is another example, which is more on the physical side. You have a picture on the left of Reese Witherspoon, and if you put glasses on that image, then the network misclassifies it to some other name, other actor. Similar examples with the glasses. If you have a person on the left, Lujo Bauer, and put some glasses on him, the network misclassifies him to John Malkovich, right? And one thing I wanted to mention here is, we're talking about adversarial examples. We're talking about adversarial attacks. However, as we're going through the lecture, I'll also be mentioning the corresponding certification problem. So not only generating inputs that are unwanted, these adversarial examples, but also stating the problem a little bit of, what the problem would be if you want to certify the network that there are no adversarial examples. So for example, here, we may have the corresponding certification problem, which is that no matter what color glasses we put on the image on the bottom left, it is not possible for the network to misclassify it to some other label, right? For the geometric transformations, it would be that any rotation between, let's say, -5 and 5 degrees cannot fool the network, right? And there is a non-trivial number of rotations, potentially an infinite number, because we're dealing with interpolation here when we're working with geometric transformations. It is another setting where adversarial examples can happen. This is the setting of reinforcement learning. And here what we have is the following situation. We have an agent, which is represented by a deep Q network, right? And what this agent does is it plays the game by looking at the image only and selecting the actions that that should be taken, the right action that should be taken. And right, so let's see here. Let's use the annotation. Okay, so over here what we have is the following image, and ideally what you want to happen is when the bow is over here, we're playing this honk, and what you want to happen is that this paddle, the correct action here is that it goes down, right? This is what happens, and this is the action that it should go down. And so when the deep Q network sees that image here on our left, it should decide to move the paddle down. And it decides this, right, once it's trained correctly, which itself is non-trivial, by the way, for reinforcement learning, but let's say that it's been trained correctly and it's been trained well and it makes the right decision. Now, what can happen is that an attacker can come, let's change the color here, can come and they can perturb this, this image on the left into another image on the right. And then once we get perturbed, like the image on the right, which again, observably looks pretty much the same, what can happen is it can fool the agent represented by this deep Q network into not doing anything. So it may just decide to do nothing, like take the no action. So that paddle here will just stay where it is, and then one would lose the game because the ball will just go behind the paddle, right? So what happens here is that the attacker again can perturb an image and fool the network and fool the classifier, or fool the agent in this case. And this setting is a bit different in the sense that while we're still perturbing images, there is many of those images taking place as the game progresses. Once an action is taken, a new state is obtained, and then the agent is asked again to make a decision. So here again, adversarial examples can take place, and there's been various works for generating adversarial examples in reinforcement learning, like this paper below that I cite, and papers which are defending building networks which are resilient to adversarial examples. And we recently also looked at the corresponding verification problem and probable training problem. So what is the certification problem here? It would be that within some range of changes that you can make to the image, so within some range of changes that you can make to the image, it is probably so that the deep Q network would always take the right decision, which is down here, right? So if you train your agent correctly to be defended against adversarial examples, or probably defended, then you may be able to prove that you cannot fool actually the agent by making this kind of perturbations. Okay, so let's move on and see some other examples. Here's another example in the natural language processing setting. Here we have text, some text about the Super Bowl in black. It says Peyton Manning became the first quarterback ever to lead 2 different teams, and so on and so forth. And when you have that text and you ask the reading comprehension system, a deep model, to answer the following question: what is the name of the quarterback who was 38 in Super Bowl 33? Then the model will correctly predict John Elway based on the text in black in bold. However, if you add this adversarial text here in blue, right? Some text here that says quarterback JFD hit jersey number 37 in Champ Bowl, some other 34, then the model actually mispredicts the answer to the question. Okay, and so we can add such kind of adversarial text, some kind of distracting text, to fool the model and get it to behave incorrectly and desirably. Okay, let's look at one last example here. So in this case, what we have is a speech-to-text translation system. So it takes speech and it translates it to text, right? So this was a work that attacked those kind of speech-to-text systems. So basically, what happens is, so let's use our notations again here. So what we have is we have the original recording over here on top. We add a little bit of noise. We add a little bit of noise here, and we end up with a new recording over here. So the original recording, gets correctly translated to the following text. It was the best of times. It was the worst of times. We add a little bit of noise, and what would that noise be? This would be, for instance, a reduction on the volume of the sound in the original recording, or we increase the sound a little bit, but very, very little bit, imperceptibly so, or maybe even perceptibly, but very little bit the volume, and any human pretty much would be able to recognize be able to translate the sound into the original text. However, the deep learning system can be fooled in this way and start producing incorrect translations, garbage translations. For instance, it's a truth universally acknowledged that a single, which doesn't make sense, right? So here we again have nicely this setup, which is we have some audio recording, right? And then we have to, typically what happens is that this recording gets pre-processed by some pre-processing stage, and then the result gets fed into the neural network. And so when you are attacking the when you're generating these changes, for instance, in the volume, you would be making changes to the input of the preprocessing state, to the preprocessing stage, not just at the input of the network, right? Okay, so what would be the corresponding certification problem here? It would be that within some range, for instance, of volume changes, of sound changes, like if I make it a little bit louder or a little bit lower, then the network would still be probably behaving correctly on those within that range, right? So you may be able to prove this. And only recently we and some other groups have started investigating this certification problem in the context of neural audio processing. Okay, so let's look at a variant of this, a simpler variant of this, which is just a similar problem. Again, audio processing. Again, you have speech to text, but this time it's just speech to classification. So I have a bunch of output labels, for instance, stop, go, left, right, up, down, and so on. And once again, I can have some original audio recording as 0. It would go for some pre-processing, then it would get fed to the deep model. Could be some LSTM, which would make a classification decision. And once again, I can try to fool the model by changing the volume, the decibels in this case, of the original sound recording, right? And this is also just like in the previous case. You can generate adversarial examples here as well. That would be not something that would fool a human. So now you get a bit of an idea that adversarial examples can exist in different settings. So audio processing, geometric perturbations, physical changes like glasses, and reinforcement learning. And for each of these, for the problem of generating adversarial examples, there is the corresponding problem of certifying the network, certifying the model that it lacks adversarial examples within some range, of course, of the original point. Okay, so just to give you a little bit of a history of this, of how adversarial examples came about. So somewhere around 2006, nearly 15 years ago, deep learning models gained renewed interest. People start investigating it more, and somewhere around 2012, various work showed that these deep models can achieve very good performance, sometimes even better than humans, largely thanks to the very good label data sets, such as ImageNet, for instance, and the increase in processing power, in hardware processing power in the form of good GPUs. And so later on, somewhere around 2013, given these advancements in between 2006 and 2012, and of course all of the advancements much earlier in the early years of neural networks, community and industry also started looking at how to use neural networks for all kinds of tasks. So, for instance, in autonomous driving, right? And so it became interesting to understand how these neural networks make decisions, right? What they make decisions, but how do they make these decisions, and gain a much more deeper understanding of their operation. Somewhere around 2014, Szegedi, while trying to understand decision making, actually discovered adversarial examples, and around 2015 and on, finding these adversarial examples, defending networks models against these in experimental defenses or probable defenses, became an active research area in all kinds of domains like audio, geometric, video, and many more. Okay, so that's roughly how things went on over time. Now, one interesting bit here is that these adversarial examples were discovered, they exist, So one thing that we would like to have here is to have robustness against these unwanted inputs. Ideally, we would want something like the network to be robust, to be behaving correctly in a sense, so to return correct outputs on all the possible inputs that it can take. Now, generally speaking, this is very impractical because the domain of the input of the neural network is infinite or very large or unbounded in most cases. So this space cannot be covered. And so what the community kind of focused here is more on a metric called the local robustness of deep models. And local robustness informally states that a model is locally robust if it returns correct outputs on some inputs that are similar to the ones that it has seen. Okay. So within some range, somewhere close, that looks very similar. And people believe that this was actually true if you obtain high accuracy on the test set. And now the question was, why is this high accuracy actually not enough, right? Here in the standard setting of training and testing that we have in standard machine learning, inputs in the training and the test set are taken from the same distribution. And the standard training aims to achieve high accuracy on the test set that is drawn from that distribution. The problem is that even though you get high accuracy, there may still be many very, very similar inputs to the one that you trained or tested on that may have, for instance, low probability, low measure under the distribution, and so you may have actually never seen them during training or testing, right, with the data sets that we have. So one question that this begs really is, well, we haven't seen them, but it still performs well on some unseen data, maybe just not these adversarial examples. And so what is actually going on? What is the model actually learning, right? So this question is very relevant, and various groups are exploring it, right? And here is this kind of mentioned this funny story in the connection between adversarial examples and Clever Hans, which was a horse that many people had thought had actually learned to perform arithmetic tasks like addition and subtraction. And so a person would stay there and they would show the horse arithmetic tasks, and then the horse would solve these tasks, these Clever Hans. However, at some point, they decided to slightly perturb the input that the horse sees, and they removed the face of the person who was present there. And then the horse turned out that couldn't solve arithmetic tasks anymore. So the moral of the story is the horse had actually learned to recognize clues, like social clues from the person, and based on that to make a decision on arithmetic tasks, and not to actually learn arithmetic. And this is one possibility that with adversarial examples, actually the model is not learning what you think it is supposed to be learning, but it is learning some perhaps unimportant features using which it makes decisions. And so when there are slight perturbations, then it starts making mistakes, just like Clever Hans. So this question about what the model learns, what features, and what it understands, it's still something that is very important, very important research question. Now, again, we can ask this question of why actually do adversarial examples exist more technically? Why are they there, right? And there are a bunch of hypotheses on this, ranging from the data set to the network to the model and so on and so forth. One hypothesis here that we'll look at now is that the neural networks are in fact too linear. So they're made up of affine transformations and some activations like rectified linear unit and tannate, sigmoid activations. And if you look at these activations, you'll see that, for instance, the RIAI on your left here you see that this is a piecewise linear function. So linear, 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 and some break, and then again becomes linear. Same kind of with the max out, and even the sigmoid, right? Here, if you chop it up like this with the red lines, you see that it's not quite piecewise linear, but it looks almost like this. And why is that? Well, they cannot be fully linear, right? But why are they designed to be kind of like mostly linear? Because linear functions are, in fact, easy to optimize. Now, let's see what happens here. So let's look at these points here on our left with the green and blue points. We have a bunch of points, and here we have a linear classifier that separates the points. Okay, so we have that. So this thing about the linearity was explored both in Goodfellow early works as well as Madri's 2017 paper, which you can take a look. These plots are taken from there. So on the left we have these points, a linear classifier separates them, that's fine. Now, if you look what happens in the middle here, right, we have a bunch of points. We still have these black points here, the circles, but now we put some boundary around them, some boxes around each point, around which we believe the points should still classify the same way as the center of the square. Now what happens is, if you just have a linear classifier, what happens is that there are some points there in the boxes that should classify as the center of the box, but because the classifier is linear, it is not able to actually obtain the right decision boundary. So there will be some points here, like the top right, top star here, top right star here in that region, that would get misclassified, and similarly for the the upper left corner of the blue square here, right? And so this model here, very linear model was actually not powerful enough to fit the data properly. So it did not fit the data properly. And the smaller the model is, as argued in the Madrid 2017 paper, the smaller the model is, the more linear it is. Bigger models have more capacity, and so they can fit more complex nonlinear decision boundaries. If you go here on the rightmost picture, here, what we have done is we have performed some form of adversarial training, which essentially is training not only on the full circles here, but also on points which are inside the squares around this blue dot, around the dots, the green and the blue dots. And so what we can end up obtaining is, instead of the linear classifier, which suffers from these adversarial examples, these regions here in the middle that are in the red stars, what happens now with the adversarial training and potentially a larger model is that you can obtain a nice, a more complex, of course, decision boundary here in red, right? And so, more nonlinearity allows you to get rid of potentially of some adversarial examples and fit the data better. Right? It is a nice investigation which was performed in this classic 2015 paper, one of the early papers by Goodfellow, Schlenz, and Segedi, right? So what we have here is we have the following setting, right? Again, we're studying the linearity of the perturbations. And so what we have here is, so let me take the annotation here. Okay, let's just pick some color, maybe some, okay, let's pick blue color. And so what we have here is on the x-axis, we have some perturbation. So over here we have we're going to be exploring some perturbation of a given image. So we are given an image with the digit 4 here. So we only have one image with the digit 4, and the correct label for that image is the label 4, right? So on the x-axis, we're going to be perturbing this image by some epsilon amount, like 0, 5, 10, 15, and so on, right? And then on the y-axis, we are going to see how the logits of the network change for each of these perturbation of the image 4, So the logits are the values that you obtain right before you do the softmax. So this, you can think of them as some form of unnormalized probabilities. And what we have here in the middle is 10 different lines, right? For the 10 different digits that we can obtain in our classification problem. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So each line represents one logit. So essentially, you know, how does the, so let's pick a line, for instance, the green line over here. Okay, so we have the green line over here, this one over here, okay. The green line over here. This is for the classification 1, so logit 1, right? This is the entries that you see in the logit for classification 1. So we see that you see how it changes with the perturbations here to the original image. And then for each logit we have a function like this, right? So we can see how the particular logit changes as we perturb the image. Now, what is interesting here? Let's take a circle. Actually, is over here. What you see is that somewhere around here, right? This is the logit, the behavior of logit 4 as we are changing the image and perturbing the image for the input image. And what we see here is this is the place pretty much where the network behaves correctly. Now we perturb the, where is the, this one here. Now we perturb the, it's here, let's say we perturb the input a little bit here, perturb it, we drew it a bit, no, maybe it's too big here, maybe it's like something like this. Okay, yeah, something like this, very, you know, some perturbations around the 0. And what we see here is that the image gets classified correctly, but there is some non-linearity happening here, right? There is non-linearity going on, and over here, right, in this region, and only when there is non-linearity going on is when the classification happens correctly. In all the other places where there is linearity happening, like over here in this part of the plane, and then over here, and then over here, you know, in these ones here, the classification is incorrect. So the 4 gets classified to some other value. So over here, for instance, it's classified to this light blue line, which is 5. So over here we have 5. This is the classification. And over here up top, over here in the left on that side, I guess this is the brown line. This would be classified as 8, right? Okay, so this is just another experiment which aims to relate this non-linearity to the lack of adversarial examples and where the network behaves, the model behaves robustly. You can actually do this experiment yourself. You can just take an image and start perturbing it and draw the corresponding logits. For each logit, you obtain a function like this, and then you see how it behaves. Okay. Okay. So this is one concept here of nonlinearity, essentially to avoid adversarial examples or to reduce the chance of adversarial examples. You may have to deal with more nonlinearity. Okay. So let's. Gives you a little bit of an idea. Okay. And I should mention, this is an active research area, right? People are trying to figure out, different research groups are trying to figure out why adversarial examples exist, both in terms of the capacity of the network, the data sets, different application domains, and so on and so forth. Very interesting space. Now, though, what we want to take a look at is how do you actually generate adversarial examples, right? I have my model, I have my deep model, and I have some input that potentially behaves correctly, like it gets classified correctly, and you know, how to actually generate these adversarial examples. And let's begin. We're going to start looking at some algorithms for doing so. So there are generally 2 types of attacks for generating adversarial examples, called targeted and untargeted attacks. Right? So a targeted attack essentially aims to misclassify the input, for instance, an image, to a specific label. So you have a specific bad label in mind, call it an adversarial label, and you try to misclassify this input. So the input gets classified to something good, like a panda, and you try to trick the model by changing the input so that it gets classified to something else, like a gibbon. With the untargeted attack, you don't have a target label in mind. What you have is, what you would like to do is to have the network classify the image to some other label than the original one that the label was classified to. So for instance, in our example with the panda bear, it would be, we would want to change the label from panda to just some other animal, whatever other animal it is, doesn't matter, just so that it's not a panda. So the optimization problem for these targeted and untargeted attacks is actually slightly different. One minimizes the loss, one maximizes the loss, but it's still an optimization problem. So typically with gradient optimization. Okay, so let's take a look at the targeted attack, how that works, and what the problem statement is. So what we have here is we're given a neural network F, okay, and the neural network takes input from some domain X and maps these inputs into some range C. So we are given a neural network and we're given an input X in this domain. And what we're also given is we're given a target label T. And what we do know is that this target label T is different from the label that the input X is classified by the model F, right? Otherwise, if it's classified to T, there's nothing else to do. So that much we know. And what we want to do, what we want to obtain here, we want to obtain a perturbation eta here, such that when I change the input X with this eta, X plus eta here, the adversarial examples, the adversarial example, then the network F, the model F, classifies these adversarial examples as T, okay? So that's the targeted problem statement. And the untargeted problem statement is basically the same. Again, you have the network F, again, you have an input X, but this time you don't have a target label in mind. You're trying to find a perturbation here to the input such that it gets, which it classifies differently than the original input X, right? So these are the two targeted and untargeted. One quick point here is that there is another classification on these attacks, not just targeted and untargeted. It is essentially how much do we know about the model, about the deep model, and depending on how much we know, we can employ different kinds of attacks, how much we can observe. So white box attackers, like what? White box attack, essentially the attacker knows everything. They know the model, they know the parameters, they know the architecture, they have the data. With a black box attacker, the attacker may know the architecture. So it may know that we have an affine layer followed by a a sigmoid layer followed by a REU or some other combination, but they may actually not know the weights. They may not know the parameters of the network at all. And so there is just a note here, just to keep in mind. What was found is actually, what's interesting is these adversarial examples are transferable. So what it means is that if I have a network, like I have some model, which I have trained with some data, right? And the attacker has no access to this network, right? But they may know some of the layers, some of the architecture, maybe all the architecture, maybe some of it, most of it, let's say. What the attacker can do, if they have access to the data on which the original network was trained, they can train a mirror network, right? And this mirror network will typically have different weights than the original network for various reasons. Even if the data is exactly the same and the architecture is exactly the same, you may not know for how long the original network was trained, what optimization method it used, so on and so forth. So the two networks will typically have different weights. But what's interesting here is that now, if you find an adversarial example to the mirror network over which you have full access using a white box method, then you can take that adversarial input and try it out on the on the original network. And in many cases, this would actually work. And so it's not guaranteed to work, but turns out that there's this concept of transferability of adversarial examples from one network to another network. Right? So one interesting question here is, you may think about this already, and that's why I put this, I started discussing it early on about certification. And the interesting question here is, well, we have transferability of adversarial examples, so that's just transferability of points, concrete points. And the question is it true that the certification, the convex shapes that we actually obtain, the proof, if you like, of obtained for one network, let's say for the mirror network, actually holds for the original network, right? So you don't have to recompute this proof. That's a very interesting question. So we started looking at it. I think it's quite interesting whether there is actually transferability on proofs as well, right? Not just on adversarial examples. Okay, and so in this lecture and in general in the course, we're going to be mostly looking at white box attacks, not black box attacks. And if we mention some more black box attacks, I'll explicitly say that. Okay, so let's look at perhaps the most well-known white box attack. This is the FGSM, targeted FGSM, which is the targeted, stands for fast gradient sign method. And let's see what happens here. So let's just use the marker again here. And let's see. So what happens here is we are given an image X. So we're just going to be using images as an example just to illustrate our points. So we're given an image X. And what we want to do is we want to compute the loss of that image X with respect to the target label, right? With respect to the label that where we want to drive the network to classify X2, right? That's label T, the target bed label, right? And so what we'll do is we're going to do the following. We're going to compute the gradient of that loss function here, okay? But this time with respect to X. So in the standard machine learning training, you typically compute the gradient with respect to the weights of the network, because that's what you're aiming to change, to find weights which minimize the loss. And here, what we're going to be trying to do is we're going to try to find, and change to X, perturbation to X, which minimizes the loss. And so the gradient with respect to the input X. Okay, so the gradient is computed as a standard. There's nothing surprising here. So it's the gradient of the loss with respect to each component, each dimension here in the input X. Okay. So once the gradient is computed, call it G. Okay, so once the gradient is computed, call it G. What we're going to do is we are going to look at the gradient. We're going to look at each entry, right? So we're going to look at each entry. And we are going to determine whether the entry is negative, 0 or positive, and then we're going to set the corresponding sign. Okay, so we compute the sign. And what this sign represents informally is this is the direction in which we are going to be optimizing, moving each pixel, each component of the input X. So sign essentially gets you the direction of movement for each pixel. Okay, and so once we get the direction of movement for each pixel, so here we get the direction sign, we get the direction of movement for each pixel. What we do is so negative direction, nothing, or positive direction, right? What we do, we are going to determine the step size. By how much are we going to be moving in that direction? And in this FGSM, this is given by the epsilon parameter, which is set a priori, typically to a very, very small constant, like let's say 0.007. Okay, so we are determining the direction, we are determining the magnitude, and then we compute the perturbation eta to the original input X. Because we are trying to get the network to classify X to the target bed label T, we need to try to get the loss to be 0, to be as small as possible, essentially, to minimize the loss. right? Because we are trying with respect to t, because we are trying to get the network to classify XST, the model to classify XST. And so what we do here is we subtract the value of the perturbation from the original input text, because we are trying to minimize the loss. Okay, and so what you see here is that each pixel is moved with the same amount, maybe in different directions. Maybe it doesn't move, but when it does move, it doesn't move because there is a 0 there. But when it does move, they move with the same the same equal amount. Okay. So once you compute the perturbed input x prime, you can check whether this is an adversarial input by checking whether it classifies, the network classifies the x prime t. And if it does, you're done. If it doesn't, you can go back again to step 1. Traditionally, FGSM is just a one step like this, but you can also perform iterated FGSM by just doing this 1, 2, 3 multiple times. Okay. So FGSM, as I say here, is designed to be fast. It's not really designed to be optimal, to find the smallest perturbation or anything like this. And this actually can create problems, as we'll see down the line. So this is the targeted FGSM method. This is the core component in various adversarial tasks, let's say. So this standard FGSM, you can also do iterated FGSM. All right, so let's move on to the next. Okay, the untargeted version is conceptually similar to the targeted FGSM. The only difference is with respect to what label is the loss. So over here, before it was with respect to this T label, which is the target bed label, but this time we're going to make it with respect to S, which is the good label. So X is correctly classified to S, and our goal, just like before, we compute the perturbation. Now we compute this perturbation just like we showed on the previous slide. No difference. This time is with respect to S, and the key thing is here is that now what we're trying to do, we're trying to maximize the loss. Why are we trying to maximize the loss? Because with respect to S, because we are trying to get the model to classify the input, the new input, to some label which is different than S. So we want to get away from S as much as possible, right? So the loss, we try to maximize it. And this is the difference in the optimization. One tries to minimize the loss, one tries to maximize the loss, okay? So that's what we try to do. Once again, we can check if we succeeded in driving the, discovering an input adversarial example X prime, which gets the model to classify it to some value other than the correct label S. And if so, you're done. If not, you can again go back to do this iterative process again. Okay, so this is targeted and untargeted FGSM, basically gradient-based optimization with respect to the gradient, with respect to the input, not with respect to the weights. So again, in standard training, the input is fixed. You're changing the weights to minimize the loss. With these attacks here, targeted and untargeted FGSM, you are fixing the weights of the network, but you are changing the input to achieve these objectives. Okay. Let's move on. So using this FGSM, this is how we obtain this change of the image so that the classification became not Panda, but Gibbon, right? And this is done using these techniques, and you can try it out yourself, see if it works. Okay. So one issue here with this FGSM business is that, as you can see, there really isn't any notion of distance, right? You are taking the original image, you are perturbing this image, and you may perturb it actually, especially if you do multiple iterations, you actually may perturb it a bit too much, like the one in the middle here, and that you may not even recognize, or you may perturb it like the one on the right, which may actually not be necessary to perturb it so much, because typically all the pixels get perturbed, but it's not clear that you actually need to perturb all the pixels by the same amount, like this magnitude. Why does it have to be the same, right? So FGSM can sometimes produce these images that are not very nice, or very distorted images as well. So the fundamental problem here is what we'd like to do is we would like to perturb the original image or the original point. Now, could be an image, could be an audio wave, could be something else. Perturb it, but only within some distance. We don't want to perturb it, but not too much, let's say. So we need some notion of distance. We need some way to capture distance between points, between inputs. Okay, and this brings us to LP norms, which are one way to capture distance between these inputs and to define similarity between points. We already looked at this in the exercise, I believe, in last, it's a recap material. But essentially what happens here is that if you want to compute the LP distance between two points x and x prime, two vectors, then what you do is you take the component-wise difference, you take the absolute value, so you compute the magnitude of the difference, you raise that to the p degree, and you do that for each component, right? This is what this equation here says. You sum them up, and you take the p root of the sum. Okay, and so we can compute like this, distance, LP distance between 2 points, right? And if the LP distance between 2 points is less than some epsilon, then we may say that the inputs are similar. LPs, just to note, is just one definition, and it's interesting actually to define metrics for visual similarity. This is just one of them here that has been used in the research literature. So for instance, if we pick p equal to 2, you'd end up with the Euclidean distance between x and x prime, right? Now, by far, the most commonly used norm is the L infinity norm. And what the L infinity norm does is it captures the maximum of the absolute values of the entry. So it captures the maximum change that that can happen to the original input. And so what it does is just iterate again component wise. You take the absolute values, the absolute change, and you take the maximum one. So that's the L infinity norm. And if you wonder how to go from the top equation, this is not something that we're going to be looking at. But if you want to know how to go from like this equation over here, to this one over here, okay, for L infinity, then you can take a look here at this link. There is a very short proof how to go from one to the other, so that you can obtain this equation for L infinity norm. So I should mention again that this is probably the most commonly used norm for adversarial example generation, adversarial training, certification, and so on. And some people argue that it, naturally captures similarity and human vision, because essentially it perturbs every pixel by a little bit, as opposed to some other changes like brightening and lightening attacks, which can change some pixel by a lot. But this is a fairly frequently used norm. So let's just see. I want to give you an example here, just to get a bit of an intuition how this would be. So let's do the following. Let's suppose that we have something like we have a point x. Okay, so this is our original input, some image, and then we have some value. Let's say 0.6, 0.8 here, and so if I want to capture all points that are, or all images or all inputs that are within some L infinity norm of distance at most 0.1 from x, then now what I would do is the following. So I would say for pixel 1, which was 0.6, I want to capture the maximum change, right, within some range. And so what I would do is I would say, now the values of P1, because it's 0.1, can range between 0.5, 0.5 and 0.7, right? And so the epsilon of 0.1 is essentially the radius of the bow here. And then P2 is going to be 0.7 and 0.9, like this. Right? So this P1, P2 are now intervals, and they capture all of the images that are within L infinity, L infinity distance of at most 0.1 from the input X here. Okay. So one other interesting thing here is, again, we have the, we have these ranges here. What's nice about it, these are simple constraints, right? That P1 is in some concrete range, P2 is another range. And if you want to do certification, this you need to consider essentially the, these boxes, this hyperrectangle here, and propagate this conjunction of P1 and P2 for the model, for the network, right? Which is easier than if you were dealing with L2, where you'd need to have quadratic constraints and maintain nonlinearity for the network. This is also why potentially certification of L infinity perturbations within some range, some distance, is easier than L2 certification of L2 norm. Okay. All right. Just shift this one here. It stays on the slide. All right. So we have this example here. That's good. I hope that it is clear what the L infinity norm is, because we're going to be seeing it in various places throughout. So this is for epsilon. Just well, let me just put it here. This is for epsilon. Epsilon 0.1. Okay. So let's continue here. All right. Now, as I mentioned already, we mentioned that FGSM sometimes can produce distorted images, and it's not something that you want. You want more smooth, more nice images, right? Or more nice perturbations of the input. Okay. And so what we would like to do is we would like to perform targeted attack, but this time with small changes. Like I want a small change to the input X as possible. So you again have the same setup. You have the neural network F, you have the input X, you have the target label T, again as before. So the setting here is exactly the same as before. But now in the output, what I want is I want to find a perturbation eta, such that, again, I classify the perturbed example as the adversarial example as T, but also that I minimize the, the eta, the norm, the P norm of eta. So I want to make eta such that the P norm is minimized. So it's as small as possible, right? Okay, so P is typically, L0, L2, or L infinity, often L infinity norm. Okay. So let's look at the optimization problem here. What would be the corresponding optimization problem more formally? So what we have here is we have the following situation. We have our goal is to find eta, where we minimize the the norm here, the P norm of eta, right? Trying to make it as small as possible, such that, and the network classifies the adversarial example to this target label T, and the resulting adversarial example, this X plus theta, is in some range, right? It's in this 0, 1. So every pixel, if you like, is in the range between 0 and 1. So that's what we would like to do. Now, the difficulty here is that this constraint is actually, in fact, everything here is hard to optimize for. But let's start with the first one. So this constraint here in red, this f of x plus eta equal to t, is a hard discrete constraint, which is difficult to optimize with gradient methods. And so one thing that you may want to do, and you'd like to do, is to replace this hard constraint with potentially a soft constraint. And here what we're going to be discussing through the rest of the lecture are the attack methods of Carlini and Wagner, summarized in this classic paper from 2017 on attacking neural networks. Okay. So let's take a look what happens here. What are we going to do? So we have the optimization problem. That constraint, the f of x plus eta equal to t, is hard to optimize for. So what we'd like to do is we'd like to replace it with potentially a softer objective. So we're going to be doing two simplifications to that problem, right? One is this dealing with this hard constraint, and the other one is dealing with the eta, with the p norm of eta when we're dealing with L infinity, which is also hard to optimize as well. But let's start with the first problem of dealing with a hard constraint. So what Carlini and Wagner explored is this idea where you're replacing the hard objective with a softer objective, so this opt-t, and the softer objective has the following mathematical property. It says that this function here, this opt-t of the adversarial example x plus eta, if it is less than or equal to 0, right, then you're guaranteed that x plus eta is an adversarial example, that it will get classified to the label t, right? Okay. And so what they do, if you're able, if you're able to define such a opt function, we're going to look at several examples next. If you're able to do this, to define such a function, and you can rewrite your optimization problem as follows. It is just like before, except that this, now we have the combination of the minimization of the, the norm of p norm of eta and the objective function opt, which is scaled by some constant here, c. Okay, so I can define now the following optimization problem is here and try to solve this optimization problem. Now notice that this condition here in step 1 is a one-way condition. It is not an if and only if. It is possible to have x plus eta existing such that f of x plus eta gets classified to t, to the target bad example, yet the objective function is greater than 0. This mathematical definition doesn't say anything about this case. This is actually possible. Could be possible. So we're just focusing on the one-way mathematical condition. Okay, so let's look at just some example functions that Carlini and Wagner experiment with the property from the step 1. And so here's a couple of functions. One definition could be just take the standard cross entropy loss and subtract 1 from it, and we'll see in a second why. Another could be just taking the max of 0 and 0.5 minus the probability that that the model f returns the probability of class t under the model f for the input x prime. Okay, so what's the probability that x prime gets classified to t by the model f? Okay, in fact, there is a mistake in the original paper with these two loss functions that we had to fix here in the slides. So you can try to find what the mistake is. Maybe you plot it and see. Okay, so let's look at the first function here. And I have simplified the notation just a little bit so we don't carry this p, f, x, t, and so on and so forth. We just use p of t. So we just plug in the cross entropy loss for loss of t. Here we use the logarithm base 2, but that's within a constant factor of the standard cross entropy. And so if we look at this function here, if we just pick the standard, pick this log with base 2, right? What we're going to see is the following function if we plot it. And it's a nice thing that we're plotting it now so that we can very clearly see what happens. And so what we see here is that when the probability that x gets classified by f as t is where the red dot is here, where my cursor is, right? The red dot is 0.5 or greater, at that point, it will certainly get classified to t, okay, because the probability is above 0.5 or greater. At that point, the value of the function is negative or 0 here at direct dot, okay? And so that function satisfies the condition that we want, the one that we stated in step 1. Okay, that's just the way that the function is designed. So this is one function, okay? That's here. That's certainly a lot easier to optimize than this, this hard constraint that we had before. And here is another function. So Kalinin and Wagner play with a bunch of functions. These are just some of these two functions. And again, we use the shortcut here. Instead of writing p of xt, we just write p of t, just to not pollute the notation here. And so what you see here is that the objective function here is always 0 or greater, right? And it is only 0, so it stays at 0 as soon as the probability that the model f classifies x to t is 0.5 or greater, so it will get classified to t by the model f. At that point, the function becomes 0. Here is the right side of the function, okay? And so once again here, that if condition, one-way condition holds also for that function as well, right? Okay, so we have a couple of these functions, these are some proxy functions, some soft functions that replace the original hard constraint, and once you can work with more easily than the original one. Okay. All right. And so this is the optimization problem, like we had before. Step 1, we have this replacement of the original function with this objective function, and then we solve the following optimization problem here at the bottom. Okay, so it looks like if we just replace the hard constraint with this, this optimization problem over here, we would be done. But unfortunately, in practice, while it sounds, sounds like reasonable, it's not actually what happens. Okay, and so the problem here is that this term here, when the norm is L infinity, when you're using the L infinity norm, it's actually taking the max of the absolute values of the entries here of the eta, of the change. This is actually quite difficult for optimization with standard gradient-based methods. Okay. And so what we need to do in the rest of the lecture is try to see how we deal with that problem as well. So we dealt already with the hard constraint. Now we need to deal with this eta L infinity norm optimization. Okay, so let's take a closer look at the problem. So this gets a bit more technical here. And so as I mentioned already, the L infinity norm of eta is going to compute the maximum change. It's just going to take the absolute value of every dimension in eta and just get the maximum value, okay? So if we look at this example here where we have eta, just an example, we're going to use throughout to demonstrate the issues. So if I have this eta over here on the left, and I have the following vector, 0.5, 0.49, 0.48, then the L infinity norm of eta is going to be 0.5. Okay, so now let's try to minimize this L infinity function, okay, L infinity norm of eta. So that's what we're going to try to do. So how would that look like? All right. So the first thing that we need to do is we need to take the gradient of the function at this point eta, with respect to each of the dimensions, eta 1, eta 2, eta 3, and in this case it's just 3 dimensions. And right, it is clearly, you can see that it's easy to see that the gradient in the first dimension is going to be 1, because infinite small change would increase the value of the max function by that amount. Okay, so it's 1. While for the other dimensions, the gradient the gradient will be 0, and this is because a very tiny change to these dimensions would actually not change the change the max of the result of the function. Okay, so if we try to do minimization here, right, we still have some factor gamma, just like we scale as usual. What we're going to end up with is the following situation. So after one step here, in the first step, we're going to take the original eta, and then we're going to subtract this, this value of gamma. Let's say the gamma is 0.03. We're going to subtract this from the original eta. We're going to end up with this vector here, the new vector 0.47, 49, 48, and so on and so forth. If we continue optimizing like this, after the second step, we're going to take, the first, the 0.47, 49, 48. We're going to observe that 49 is actually the maximum value here. We're going to reduce it, and we're going to end up with 0.46 in the second dimension, and so on and so forth. Now, because the gradient is actually non-zero, it's non-zero only at the max location and zero everywhere else. There are two issues here. So one is that we are essentially, very slowly converging here. We're only modifying one dimension at a time here. And the second problem is that this optimization, this minimization of the L infinity norm interacts with the other parts of the objective function, this opt function, this proxy function that we discussed before. And there is no penalty anywhere in the optimization that prevents this optimization of the opt function from pushing the values in eta back up higher, okay? And so one will end up, as we'll see, one could end up in these oscillating scenarios where we are minimizing eta, but this other optimization, this opt function actually can push it higher. So we have several issues. One is this interaction with opt minimization of the opt function, and the other one is that we are very slowly only modifying like one dimension at a time. Okay, so this makes optimization of this L infinity norm with gradient methods difficult. Okay, so let's see this oscillation problem. What can happen here? Okay, so now we're looking at the full optimization problem, which also include this opt function, right? Remember let me just highlight here. Over here, this is the opt function for which we had several proxies. We looked at two choices for the opt function. The paper of Carlini and Wagner looks at other proxy functions as well. Okay, as we saw already before, after one step of gradient descent here, we're going to end up with the following new value for eta, okay? Now the problem is, what can happen is within this, still in this big first step, the optimizer can actually bump up the second location because it's trying to optimize the opt function. So it may actually, nothing prevents it from increasing this 0.49 to 0.5. Okay, and so it may bump up locations up and down like this, and that can happen. That's fine. But then after the second step, right, you may actually, because this is the highest one. It was the highest one, 49. But then, after the second step, the minimization of the eta is going to try to reduce this to some value here, right, 0.47. But nothing prevents the optimizer, when it's optimizing the opt function, from actually increasing this 4.7 here into this 0.5 here. So one dimension may be reduced, this second dimension may be reduced because we're trying to minimize the eta, this L infinity norm. And the other one may be increased, the other dimension may be increased because we're trying to optimize this opt function. Okay, so what can happen here is that you can end up with this oscillation and bouncing around. Okay, so it may not be so great to optimize this L infinity norms, minimize it, especially when there's other terms in the loss function. If you try it in practice, this is something that you can observe. Okay, all right, so I hope you get the intuition for why gradient descent may struggle with minimizing the L infinity norm, and especially when there's other terms like these opt functions, whatever functions we are picking there from our choices. Okay, so let's continue. Okay, so how would you solve the issue? Like, how would we solve this problem, right? So once again, just like we did with the hard constraint before, this f of x plus eta equal to t, we replaced it with some opt function, right, with certain mathematical property. We may also do the same thing here. So we'll try to solve the problem by replacing the this function, this L infinity norm of eta with some other proxy function that is potentially easier to optimize, but also that captures more or less distance. In some way, maybe not exactly as the L infinity, but in some parts similar, okay? So here is one such proxy function that was explored by Kalini and Wagner, and we'll take a look now. And so the idea here is the following. So we're going to be replacing, so let's just use the drawing here. Yeah. We're going to be replacing the, the L infinity norm of eta with the following proxy function, right? And what you see here is that we have a summation across all of the dimension of eta. And what we do here is just like before, just like in normal infinity, we take the absolute value of the dimension and we, subtract from it the value of tau. We'll see what tau is. Tau is some kind of ceiling here. And then we take the max of this result with 0. And, we sum this over all of the dimension. Okay. And so, this hyperparameter essentially, but it actually changes during optimization. Essentially, when the whole thing finishes, we'll see it will define some L infinity bound. Okay, it will define some L infinity bound when the whole thing finishes. So initially, when you start the process, right, tau will start at 1. So now you see what happens. If tau starts at 1, okay, that here is the absolute value, okay, this tau I, absolute value of tau I. So if tau starts at 1 and the values are between 0 and 1, you are going to end up with everything being 0, right? The whole thing will be 0, okay? And so what you're going to be doing, nothing is going to happen when everything is 0. And so what you want to do is you want to start decreasing this tau at every iteration. So let's say by some factor of 0.9. So initially it may be 1, then it may become 0.9, then it may become 0.81, and so on and so forth at every iteration. So if all of this eta i's and the absolute values are less, the change is less than this tau, all of them are less, then the entire expression will be 0, and then we're going to try to decrease tau to get smaller and smaller values. Okay. Here's a couple of notes that we're actually going to clarify on the next slide. In fact, under certain conditions, the gradient here is similar to the gradient, or is the same as the gradient of the L infinity norm. Okay, especially when tau is large. So now let's see, to see some of these issues, let's see how actually this works on an example. But the high level point here is that we have replaced this, eta, the L infinity norm of eta with some proxy function. And what you see here is that essentially all of the dimension of this proxy of eta I contribute to the value, aim to contribute to the value of this proxy function. But let's see on the next slide. I have prepared an example that hopefully clarifies some of these points once we see them in an real example. I think it will be clear. Okay, so actually this example was prepared based on many questions last year. So hopefully we are able to clarify some points here. Okay, so what we have here is, we start with the, let's call this L of eta, this expression here, the sum over the maxes. because we don't want to be writing it every time. And we're going to start with this eta over here. Let's see. We're going to start with this eta over here, some value over here. Okay, and we're going to be working with that. Okay, so let's begin and see how the optimization will work now with this proxy function here. Okay, so we're only going to be showing the optimization of this proxy function, L of eta, and not like the L of eta plus the opt, just to get the point across to see what happens. Okay, and to illustrate this relationship with optimizing the just the true L infinity function norm. Okay, so let's start with tau equal to 1. Okay, so obviously when tau is equal to 1 in our function will be 0, and there is nothing to do here. So we're going to be decreasing the tau when everything is 0, when all of the elements, the absolute value of all the elements in eta I are less than tau, then we are just annealing down this tau by some factor, let's say 0.9. Okay, so let's start with 0.9. If you look at our numbers here, well, again, everything is 0. So we need to anneal down more and so on and so forth. So we keep annealing down, and after some number of iterations, what we're going to end up with is the first tau where the L of eta is actually not 0. So there is some absolute values of eta I, some components whose absolute value is actually potentially greater than tau. Now let's see what happens in the first step. Okay, so we apply the function, and what we're going to get here is the following situation. This will be the value here. You'd get something like 0.014. So the first dimension is going to be less than the value of tau that we have. But the other two dimensions are actually going to be greater than the value of tau. And if they're greater, then we're going to keep them. If they're less, like the first dimension, then we just set it to 0. Okay, so we end up with this value of 0.014. And so now the question is, what is the gradient of this L function, of this proxy function, with respect to the eta? Because that's the thing that we want to change, right? And now because both dimensions, potentially all dimensions here contribute to the value, to the value of L, then for all of these positive dimensions, right, we are just the gradient is going to be 1, because like a very small change here is going to change the value of the L by that amount. While this dimension, the value here, the gradient here is 0. This entry is 0, because right, just like before. And so, as before, we can update the theta as usual. We can update it again by some factor, some lambda. We reduce it again, and we continue with the next step. Okay. So this is how this is going to work. This works. Okay. So multiple dimensions contribute. So a function is easier to optimize, and multiple dimensions contribute to the progress, to the optimization process. Few notes here. So within each iteration, right, there can be case steps. So over here, so we just showed one step, but for one iteration we have a fixed tau. So this iteration here, the tau is 0.478, and we may have multiple steps, each of which updates the value of eta. Right? Each updates eta. So we keep updating. Now, after some point, potentially, this eta is going to be the norm, the eta is going to be updated, and then it could be the case again that the eta gets small, the change gets small, which is what we want. But then let's say, if after case steps we just reduce this eta, and we still have something greater than a tau, some change which is greater than tau, than what we want, then the entire optimization will stop, right? And this is what we would get. We just couldn't get this eta to be less than the tau that we wanted, that we set here. Now, if L of eta is 0, it means that all of the entries are less than tau, the absolute values of all the is less than tau, and then optimization will continue as we showed already, times the previous tau. This we already showed before, the next iteration. Inside the code there is various stopping criteria. So if you reach some predefined value of tau here, it gets small and small and small, then you also stop. Now, so we stop like this, we go like this, we go, and then when you stop, of course, when you stop here with the eta, you can check whether you have whether you have an adversarial example or not. Now, when the optimization stops, okay, if you want to have a bound on the L infinity norm for which you actually, where you stopped, all you need to do is just look at the eta at the iteration before the last one, because that eta, we know all of the values, all the components in eta were less than tau, and so we do know that for that eta at this iteration before the current one, the L infinity norm is bounded by this tau. So we have discovered the tau, in the previous iteration, for which the change that we are doing to the input is the L infinity norm is of that change is bounded by this tau. So we know that for sure. Okay, so this may or may not, of course, find an adversarial example. When you finish here, when you terminate, you can take a look whether you have found an adversarial example or you have not found an adversarial example. And we already have one way we can test that by just evaluating the opt function and seeing if it is less than or equal to 0. And if it is, then well, you have found an adversarial example, because then it is guaranteed that this label gets classified to T. We already discussed this before. Of course, you may find an adversarial example here, even if the opt function is greater than 0, because it's only one direction, the if. Right? Okay, so this is how optimization works with this proxy function. And this is how you can get guarantees on the, you minimize this eta, but you also get guarantees on the L infinity norm here that you of this eta. It's guaranteed to be less than tau. Okay, one interesting point here is one question that one can ask is, well, the gradient here, we see it over here, is not like the gradient of the L infinity norm, because there only in the gradient only one entry was a 1, which is the maximum value, and here there are like more entries here, right? So one question is, when does the optimization behave like the L infinity norm? And the answer here is intuitively when the tau is fairly large. So when the tau is fairly large, then you would have very few entries in eta whose absolute values are greater than tau. There may be few. If it's too large, then there will be none. But as you go down with the tau, maybe you get some, like 1, 2, 3, or some of those whose value is actually greater than tau. And there you get a very sparse gradient where everything is 0, but only a few places are 1, or maybe even only one place is 1. And then you behave like the L infinity optimization. You get that kind of gradient, the same or similar. If you want to be very precise, here I have written the condition when you get exactly the same gradient. So all you need to do is you need to take I mean, that's not something that we want to do, but we're just discussing this connection now. So if I take the eta here and I take the top one, the highest value here in eta, and the second highest value in eta, okay? And then I pick a tau which is between these two, right? Then the gradient will be only one element would essentially pop up above tau, which is eta top 1, and then the gradient of this proxy function here will be the same as the gradient of the L infinity norm of theta, right? So intuitively, when the taus are large, you behave like this, like the optimization with the L infinity norm on eta, and when they get smaller and smaller, then you then you start becoming considering more dimensions and changing more than one dimension at a time, right? Okay, so this is some points here about the optimization with this proxy functions, and of course, naturally, you can think it also the other way around. If you are having smaller and smaller values of tau, which meaning more and more entries in the eta are greater than tau, whose absolute values are greater than tau, then you are more and more likely to not finish this minimization process where the L of eta is 0, where all the entries are less than tau, because there are just too many entries which are greater than tau at this point. So it's interesting, essentially, up to which point it actually behaves close to the gradient, close to the L infinity norm optimization, and when does it stop doing that? Because if you have too low of a tau, then you are more likely to terminate, because you just, after k steps, you still end up with this condition over here that we wrote, where L of eta is not equal to 0. Okay, so the takeaway points are, we have a proxy function that is easier to optimize. That's one takeaway point. And then the second takeaway point, there is more than one dimension that gets optimized at a time of the eta, and we can give guarantees on the eta in terms of L infinity norm by just taking the tau at the previous iteration. Okay, good. So let's, I hope that this gives you some idea. We also have an exercise on this topic so that we can play more with it. Okay, so in summary, we have this optimization problem. We had the original optimization problem, then we replace it with the function opt, which is a one-way implication, has the following mathematical property, and we ended up with this optimization problem over here in the bottom. And then what we showed is that, so let me just use the color again here. So first, this here is a result of one replacement of this hard constraint. And here what we showed in the previous slides is that we had a replacement also for that function. So we have two proxy functions here that we can play with to make the optimization problem easier and faster to solve. And the replacement here was such that you can actually guarantee some bound on the eta, L infinity bound on the eta that you found. Okay, with this tau. Okay, one thing we haven't looked at is over here. There is some form of constrained optimization because you want the result to fall into these boundaries. We'll look at this next time. That's also something that comes up very much in the adversarial training as well. All right, so the moral of the story here, the high level point, is that we have proxy functions that make it easier for us to perform optimization and to incorporate this idea of trying to find small perturbations, small values of eta with respect to the L infinity norm, and that produce nicer images. And as we'll see next time, they do actually produce nicer images because the perturbations are smaller to the original image X. All right. So in summary, what we covered in this lecture was we looked at examples, more examples in various application domains of adversarial examples like audio, geometric perturbations, reinforcement learning, natural language processing, speech to, in the audio setting, we looked at speech to text, and then we looked at speech to classification, just stop, go, up, down, and so on. In the process, I mentioned both the adversarial example generation problem, but also the corresponding certification problem that arises in these application domains. And one thing to not forget is that we are dealing not just with the neural network, but with the entire pipeline of geometric transformations, for instance, rotation, translation, shearing, and more, and their combinations, of which there is an infinite number. And we're also dealing with preprocessing in the audio space, in the NLP, in the computation of the embeddings, and so on and so forth. Okay, so that was that. Then we looked at some reasons for why adversarial examples exist. And one particular point we looked at was linearity, non-linearity, and we discussed some investigation which said that when the model behaves too linearly in this classification for the particular input, then you get adversarial examples, and when there is more non-linearity, then you are less likely to get adversarial examples. These are just some investigations, and this is pretty much an open area of research. And then we started looking at techniques for generating adversarial examples. So we looked at fast gradient sign method, both targeted and untargeted, one-step FGSM, where we had minimization of the loss function when we have targeted, because we want to drive it to a particular target label, and we had maximization of the loss function when we're dealing with an untargeted, because we want to get away from a particular label. Okay, one of the issues with FGSM turns out is that because there is no notion of distance, how we are perturbing the input, every pixel is pretty much perturbed by the same amount, you can end up with images that are not so nice, too distorted. And therefore, we started looking at how to generate images, adversarial inputs that are nicer, not so distorted. And there we had to incorporate the notion of a distance. So we needed some notion of a distance, like EUP norms, and specifically L infinity norm, which is one of the most used norms. And we started looking at other methods for generating adversarial examples, which try to minimize the perturbation. Specifically, we looked at Kalinin and Wagner's attacks, some of them. And the core idea, the high-level idea there was to replace the difficult to optimize hard constraints, of which there were two. This was the hard constraint of getting the model to classify the perturbed image to a given label T, and then the minimization of the perturbation, the L infinity norm of the perturbation. And the core idea was to replace these constraints with easier to optimize functions, so that we can have a higher chance to solve this optimization problem. So this is so ultimately a lot of this adversarial example generation, training, and provable defenses, and all of this comes down to defining a good, suitable optimization problem. So this will be a recurring theme that is going to be appearing throughout the lectures. Okay, great. So I hope you got an idea about adversarial examples. And next time, we're going to talk a little bit about dealing with constraints in adversarial examples, like how to restrict the input to be within certain range, and what optimizers to use, and continue to adversarial defenses. So I hope that you enjoyed the lecture, and see you next time.